I'm Jim Anderton, and this is the Industry Insights and Trends podcast. On this show, we'll explore the length and breadth of 21st century engineering, from civil engineering megaprojects to innovation at the quantum level. We speak with subject matter experts and industry watchers from every sector of the engineering discipline. On this episode,
will simulation replace engineers? You know, engineering used to be about literally pencil on paper. It used to be about drafting tables, drawing. There was a component of art to it. And that all changed when CAD, computer-aided design, entered, and the engineering profession turned into something which was a little more mathematical, more directly mathematical, and less about drawing pretty pictures. I'm with Michael Alba. He's senior editor here at engineering.com. And Michael, I know your beat is to cover this aspect of engineering, which is some of the advanced software that we're using to do this. But the state of the art right now, we've gone beyond just rendering things on computers, haven't we?
Yeah, we sure have. Thanks for having me on, Jim. Yeah, CAD simulation software, these big software platforms are used at every level of engineering now. I mean, you can't really do engineering without it today.
Yeah. Now, one of the things, AutoCAD was a popular platform, one of the first ones, years ago when I was breaking into the industry, and it was notable in that it seemed to require a certain mindset that was a little bit different from physically, putting a French curve onto a piece of paper and drawing it, with a pencil. You're defining line segments, curves were a factor. I mean, these things were tricky stuff. It felt like a foreign language. Is that still the case today?
I think it almost is. That mentality, the way that engineers started doing things with the advent of computer graphics and computer design, like you say, thinking about it very geometrically and drawing lines and extruding boxes and circles and just the whole process of creating shapes in CAD is now standardized, and every software does it pretty much the same way, but it's not really an intuitive way of doing it, in my opinion. And I think a lot of the cool innovations that we're seeing now are starting to push back against that very paradigm that has stood ground for the last 40 years.
Yeah. I remember early instruction used to tell us that there's really no such thing as a curve. What there are is that there are a set of line segments that are infinitesimal, almost infinitely small. And so that it's almost depends on scale. If you could sort of magnify a million times, you would see basically a very rectilinear sort of set of very, very short line segments, which sort of defines into a curve. And that's intuitively kind of not the way we think about curved shapes, is it?
No, it's the digital revolution in a nutshell. Everything's become quantized down to the pixel level. So it's all just bits down there. So you kind of have to rethink about everything you're doing in terms of those bits. I mean, the software abstracts it, but at the end of the day, that's what it is, ones and zeros.
Yeah. And it's the other aspect I think that I think lay people maybe don't appreciate about this is that when you look at surfaces, I mean, we can conceptualize surfaces in a drawing or a rendering because we live in a world of surfaces, but surfaces from a mathematical standpoint, that's a whole different ballgame. We're talking about something where, again, we're almost like pixelated, small, miniature flat planes with an infinite number of them, right?
Yeah, that's exactly what meshing is. When you want to run a simulation on a CAD model, you have in your head this 3D shape, this continuous surface with curves and everything else. But when you zoom in close enough, again, it's just these small, flat, triangular planes called a mesh.
Yeah. Now, of course, it presupposes that the more complex the shape or the form, the finer that mesh should be. Is that a general rule of thumb?
It depends on what you're simulating and the area of the shape. I'm far from an expert in meshing. There's people with decades of experience at exactly this. How should I mesh this part of the model to get the best results? So it's a bit of an art, a bit of a science. And again, today's tools are trying to sort of upend that mentality where there's tools today where you don't even have to think about meshing. Really, it's becoming, I think, a bit of a lost art. We're not there yet, but that's the direction things are heading.
Yeah. Now, in early days of this technology, I'm talking 30 plus years ago, we were a bit computationally limited. So in theory, your design could be as rough as you would care to make it, because the more detail you put in, the more computational time and horsepower it took to actually render it or manipulate it. So there's a certain constraint in that you wanted to try and make your design as simple as possible, not just for engineering production reasons, but also because it's just easier to render it. Are those constraints still there? Now can you just go crazy and do whatever you want?
The constraints are still there, but they are eroding quickly. I mean, NVIDIA, the graphics card company, which I'm sure you've heard of, just a couple of weeks ago had their annual GTC conference. And one of their pieces of news at that conference was that their Blackwell chips, their latest generation of GPUs, are making simulation, all types of simulation, up to 50 times faster compared to leading
Wow.
edge data center CPUs. So, it's a bit of a boast on their part. And whether they're exaggerating or not, I mean, it's undeniable that chips are getting smaller and faster, and more can be done with them. I mean, just look at the generative AI revolution we're in now. That's almost purely down to the computational power that we've acquired over the last decade or so. I mean, there's software advancements too, but just the chips themselves are so much better than they used to be that you can start to care less and less about optimizing what you're doing with those chips. You just brute force anything you want to.
Yeah, it's
So it's
kind of
less and
fun
less.
to pull that back to reality, because of course things like Nvidia, graphics cards, they're all over the news, but not for the reasons of graphics. It's because they're cross-purposing them for other things like artificial intelligence or high-level computers. But at the essence, I mean, if all this horsepower used for its original intent, I guess would be to render things better, right?
Yeah, and it's not an either or. I mean, NVIDIA's graphics chips were designed back in the 90s for rendering graphics on a computer screen, and they still do that today, but much, much faster. But beyond the improvements in their core purpose, combining that with AI, which just happens to use the same chip architecture or close enough, they can actually use AI to bolster the graphics rendering as it is. So it's kind of a speed up from both directions.
Yeah, yeah. People tour great architectural sort of masterpieces of antiquity. You see a medieval, church, a cathedral, and say, "Wow, isn't it amazing that the engineers were able to figure this out and create these unsupported spans, these vast arches?" Of course, what we never saw was the half dozen or so attempts to build that structure where it collapsed, because they simply didn't have the computational tools or the skills that we have today. So it was a highly iterative process. So you sketched something or you drew it in whatever technology you had at the time, you built it, and then you basically tested it. And if it collapsed, you sort of swept up the junk and you tried again until you sort of iterated your way towards something successful. And of course, everyone remembers the success, and thankfully, in some ways, we forget the failures. And we've seen that right up to the point at which simulation became a factor. And I'm thinking probably some primitive attempts to do this in the 60s with mainframe computers, but it's a world now where increasingly you don't actually get to the prototype stage of making stuff unless you know a lot more about how it's going to perform, do you?
Yeah, I mean that process you described of building it and watching it fall and trying again over and over, a lot of that is just happening digitally now in simulation software. I mean, the sort of ultimate goal, pie in the sky of all this is zero prototypes, where by the time you build it, it's going to work exactly as you want it to. And again, we're still not there, but we're getting a lot closer. The simulation software that's coming out now is becoming so much more accessible, and with AI, it's becoming much quicker, getting to the point where anybody can really use these tools to get a much better idea of the real world performance of their designs.
Yeah. Yeah. Now it's computational fluid dynamics is particularly interesting to me, because that's something where taken to its limit, you can imagine a world in which there's no such thing as a wind tunnel anymore, because you're going to use advanced AI possibly to design that wing. You're going to test it or simulate it virtually and then run it through enough CFD so that you can validate the thing and then just go build an airplane wing. Is that where we're going in this future, where basically testing itself disappears?
What you've just described is not the future. That's today. In fact, that's last year. NVIDIA partnered with a CFD company called Luminary Cloud to develop a virtual wind tunnel, exactly as you described. So they've got this real-time interactive virtual wind tunnel that debuted. It was really a showcase last year at SC24, but this year at GTC a couple weeks ago, they announced that they are making this tech demo basically openly available. It's open source. They call it the Omniverse Blueprint for Real-Time Digital Twins. And now any simulation provider can take that tech demo and incorporate it into their own software. And we're seeing that from simulation companies today. I want to say Altair, who just recently announced that they were going to integrate that. Another company called SimScale is doing it. And so we're going to see more and more of this kind of thing as we go forward.
Wow. One thing I've certainly noticed in the aerospace industry is there was a time when you selected sort of an airfoil profile, a 4-digit or 5 series profile. Maybe you developed one on your own, and much of the span of the wing was fairly consistent. So it scaled up and down, linearly. So as the, along the chord line got smaller toward the wingtip, as the wing tapered, basically, it was roughly consistent. Now we're seeing some dramatic changes in the profile. And one thing I've noticed is the winglets. The winglets that we see frequently on aircraft today, designed to convert that span-wise flow into, a little bit of drag reduction. That's going away now. And it seems to me that the structures themselves flex considerably. Anyone who's been in a Dreamliner recently would see that it looks like a seagull in there. It almost frightens you looking out at the wing, watching the thing flex up. So you've got a combination of aerodynamic issues. You're using CFD, but also composite structures that flex a lot. They bend, they twist. So it's not like a stiff cantilever structure anymore at the same time. So are you using the same technology now to try and factor all that in? Because if you're designing something like an airplane wing today, holy cow, it's got to be aerodynamically optimized. It's got to be strong enough that it won't come off the airplane. But at the same token, it's got to have maybe 3 or 4 meters of flex up and down at the root.
Yeah, it's a big task. But again, automation is really doing a lot for this. So another collaboration that I want to highlight is Luminary Cloud, again, the company I just mentioned with the virtual wind tunnel. They've collaborated with another company called NTOP, which does computational design. So they'll basically iterate through a bunch of different parametric models, basically creating geometry, thousands of variants of a type of geometry, like an airplane wing. And now they've partnered with Luminary Cloud so that they can send that geometric data straight to Luminary Cloud's CFD solvers, run some simulations on it, and basically create a bunch of geometry, simulate all of it, see which one's best. And they're taking it further with NVIDIA again. They're sending those simulation results to NVIDIA's Physics NeMo framework. That's just a framework for training AI models. And so they plug those simulations into those AI models, and then the AI learns how to do that simulation, that CFD that Luminary Cloud was doing, so you can do it even faster and just increase the iterations even more. So yeah, it's complicated. It still takes a lot of computing power, but we can throw so much more of it at it now that those problems become easier to solve.
Yeah, and Michael, I mean, you brought up the word, and it was going to come into this conversation eventually anyway, and that's AI. It's with AI can solve the problems, but we're entering a world now where we're beginning to wonder if AI can start asking the questions. So are we at that point yet where essentially someone who, for example, is not an aerospace engineer, but finds himself in a position where he's expected to do something that requires, a CFD solution, can he just turn to an AI-based system in the future and say, look, you know what, I need to optimize this fan blade, and I don't know how to do it, so just tell me how?
That seems to be the direction that a lot of software developers are heading. They're all sort of introducing their own versions of AI chatbots that are trained specifically on their software, the manuals, the forums, years of data of how people are using their software, and basically just integrating that right inside. So if you're a user who doesn't understand how to use the software, for example, or even a deeper question, like how do I optimize this type of object, you can ask that question. And I don't know how good the results are right now. I don't know how long it will be before they're real viable answers that an engineer could take action on, but that's certainly what a lot of these software vendors want to do.
Yeah. Michael, there was a time when you made a major commitment within an engineering organization to one platform or one company, basically. And if you're an Autodesk house or you're a CATIA house, essentially, and you had to essentially go and search talent and hire people that knew your platform. Is that going to be the future as well? Do you think we're going to go cross-platform to the point where it doesn't really matter what you train on or which you use currently?
It's hard to say because the software vendors themselves are consolidating even more, right? They're just diving headfirst into the platform mentality where they want to be your single destination for every type of engineering software that you could ever want or use. So as they're trying to bring users into their platform and keep them there, there's a lot of startups now who are really trying to break that mold and offer cool new technology, particularly inspired by AI, that doesn't replace those platforms, but augments them in ways that the platforms themselves seem to be slow to respond to. So it's going to be a bit of a tug of war, I think, between different companies, and I'm not sure how it's going to shake out in the end.
Yeah. Another phenomenon I've been noticing is that it's more and more firms are trying to push some of the design and development work down to their vendor base or supplier base. So if you're buying a generator set or you're buying a power supply or something from a vendor at this point, you expect them to actually figure out how it integrates into your assembly from a sub-assembly perspective. So there's a desire to kind of decentralize some of this at the same time, but then you got a communications issue, which is now you might have 20, 30, 40 or more vendors who are all sort of interactively trying to work to create a part or an assembly that integrates with your product. Is that communication factor? Is that, I mean, we're talking now virtually. Is that the same way we're going to see engineering going to work? Are you be working with teams like all over the planet, real time?
I mean, that's again another goal of a lot of these software platforms. They're not just offering the software now, they're trying to link it all together in this one unified workflow on the cloud where everybody involved gets access to just the data they need so that they can play their part. And everybody's using the same up-to-date files. Everybody's got the same models, the same drawings. Again, these are visions that probably still have a lot of hurdles before they're fully realized, but that's where everyone wants to take it. Yeah.
Yeah. Yeah. Another example that pops up recently is the Holy Grail, of course, is everyone would love to get that score, that big contract with, say, a major airframer or a defense contractor, because, of course, the the dollar values can be considerable. But then you run into problems with classification. If it's an ITER product or assembly, if you're working on something which requires sort of a higher level of security, then you're worried about vetting your employees. Can you really outsource it all around the world, basically, if there's something which contains information that is sensitive? What I'm wondering now is that do we have a world where we could potentially theoretically dumb down or obscure aspects of a design that might be classified or contain sensitive of IP, and then still allow an individual in an open market basis to go ahead and design that bracket, or that fastener assembly?
Yeah, well, a lot of the CAD platforms offer ways to simplify models, reduce them just to sort of their external shape. So they cut out a lot of the details in there that would be considered proprietary. I mean, I'll leave the regulations to other people, but the technology seems to be there.
Yeah. It's got to come up here because right now, all over the media, anyone who's engineering professional has been watching SpaceX. Now, SpaceX has developed the world's largest rocket. Its Starship is absolutely gigantic. The entire assembly is bigger than a Saturn V. I mean, this thing is the future of heavy lift. They've also had 2 failures in a row in spectacular fashion with the vehicle blowing up. And there are some who are not engineering professionals who are commenting on this, and I see this widely, saying, yeah, but you know what? Work fast, build it, break it, redesign, fly it again. That's sort of the mindset, and that's the way to compress development time. Now, others I talk to in the engineering industry basically say, no, that's obsolete. That's what we used to do 30 years ago. The idea now is to design it, simulate it, build hardware, and then fly it successfully, because you've already worked that out in simulation, and that test failure should be relatively rare. What do you think? I mean, is this are they doing it the old-fashioned way, or is something else going on here?
I mean, I don't know, but I imagine SpaceX has some pretty modern design and simulation platforms that they're using. My guess is that it's just really complicated to build a rocket that works. So even with all this fancy technology and all the hours of simulation you put into it, failures happen, and you try to learn from them and go on. So I guess it's sort of a blend of what you were saying with the cathedrals, where you build it and watch it fall down and build it again. It's that, but also augmented with simulation and modern technology.
Yeah. Michael, last question. We've come from a world in which to be an engineer, you had to be very good at mathematics, intuitively. Then you had to know how to use a slide rule effectively. And then we moved to an era where you had to know basically how to work algorithms on a mainframe computer. And now we've stepwise advanced to the point we're at now. A lot of the mathematical workload has been taken over by advanced systems. Basically, now we've got AI on the horizon. Do you think we're going to see a world in which engineering as a profession changes or maybe even disappears? Is it going to be at a point where individuals who have no sort of mathematical or strict engineering training can jump in and leverage this technology and design things?
Yeah, I think we're kind of in that world already. You don't need to be an expert to learn how to use some 3D modeling software, to learn how to use a 3D printer. These are very accessible. Anybody can kind of start tinkering and making stuff, at least simple stuff. But as the technology gets better and better, and maybe as AI becomes more of a factor, yeah, I think anybody can do this stuff. Should they do this stuff without the training and the knowledge? That's another question. But I think they absolutely will be able to at some point.
Yeah. Awesome. It's actually a very impressive future. I can't wait to see myself. Michael Alba, Senior Editor here at engineering.com. Thanks for joining me on the podcast.
Yeah, thanks for having me, Jim.
That's it for today's Industry Insights and Trends podcast, brought to you by engineering.com. If you like this program and want to keep pace with the latest innovations in engineering, subscribe to our newsletters such as Design Weekly, 3D Printing, Aerospace and Defense, digital transformation, simulation, or a weekly roundup at engineering.com/subscribe. For our deeper engineering series, visit engineering.com TV for exclusive shows like Designing the Future, Manufacturing the Future, and the Engineering Roundtable, found exclusively on engineering.com TV. Thanks for tuning in.